In the C1 module, we looked at arithmetic sequences, where there's a common difference between each term of the sequence. So from one term to another you add 2. In C2 we looked at geometric sequences, and instead of adding a number each time, we multiply by a number each time. 5 times 2 is 10, 10 times 2 is 20, 20 times 2 is 40, 40 times 2 is 80. So the number that you multiply by each time is called the common ratio. So in this sequence, the first term is 5 and the common ratio is 2. So let's look at the theory of this. We've got a first term, a. The second term is a times r, the common ratio. The next term is a times r times r. The next term is a times r times r times r, and so on. So the formula for the nth term of a geometric sequence is a times r to the n minus 1. Why is it n minus 1? Well, in the first term there's no r, in the second term there's 1 r, in the third term there's 2 r's, in the fourth term there's 3 r's. So the fourth term has 3, it's r to the power 3. The third term is r to the power 2. So the number here is 1 less than that number there. That's because we start with no r's, and then there's 1 r in the second term, and so on. So for the nth term, the formula is ar to the n minus 1. Now in a geometric series, the terms are added together. So let's think about a series that looks like this. The nth term is ar to the n minus 1. Let's think about adding them all up. Let's call that Sn. Now I'm going to multiply everything by r. So a times r is ar, I'm going to put that there. Ar times r is ar squared. Remember, I'm taking this number here and I've multiplied it by r, so every term here is going to be multiplied by r. So the next term is going to be ar cubed. That comes from ar squared times r to give ar cubed. Plus dotty dotty dotty, I'm going to get an ar to the n minus 1, and then I'm going to have ar to the n minus 1 times by r, so that's ar to the n. Doesn't quite fit in here, so I'll do it there. So now I'm going to take these two equations and I'm going to subtract them. Let's call this equation 1, let's call this equation 2, so let's do equation 1 minus equation 2. So it's Sn minus Rsn it's a minus nothing, it's ar minus ar, that's nothing, ar squared minus ar squared, that's nothing, blah blah, etc 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 etc. That, take away that, is nothing. There's no extra term here, but we've got to take away ar to the power n. Sn is a factor on the left hand side, so Sn 1 minus r, and a is a factor on the right hand side, so therefore I get Sn equals a 1 minus r to the power n over 1 minus r. That's not the world's best n, looks like an h, but that is an n. So why is this of any use? Well, let's take a geometric sequence. Let's take a very simple one. Let's start with 4 and times by 3 every time, and let's just do 4 terms. So the sum to 4 terms is 4 plus 12 plus 36 plus 108. So we can work this out. It equals 160. You can also put it into the formula. So S4 is a, that's 4, bracket 1 minus, the common ratio in this case is 3, because these numbers are being times by 3. So it's 3 to the power n. What's n? Well, it's 4 over 1 minus r, again that's 3. So it's 4 lots of 1 minus 3 to the power 4, that's 81, over 1 minus 3, that's minus 2. 1 minus 81 is minus 80, so it's 4 times minus 80 over minus 2. 4 times 80 is 320, so that's minus 320 over minus 2, which is 160, which is what we got here. So here's a demonstration here of the use of this formula. Here's another geometric sequence. In this case the first term is 10 and the common ratio is 1/2. Every term is multiplied by 1/2. What about the series? Well, the series is 10 plus 5 plus 5 over 2 plus 5 over 4, etc, etc, etc. The nth term is 10 times 1/2 to the n minus 1. Now let's consider these terms. 5 over 2, 5 over 4, the next one's 5 over 8. When n is a very large number, this term here is very, very small. And the whole series approaches one number. It approaches a limit. Let's think about what that is. We've got a formula for Sn. Sn is a 1 minus r to the power n over 1 minus r. So that's 10, 1 minus 1/2 to the power, well, let's do it to 100. 100 terms over 1 minus 1/2. What's 1/2 to the power 100? If you do 1/2 to the power 100, I'll squeeze this in over here, I'm going to get 10 multiplied by 1 minus 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 1 minus such a ridiculously small number is 1. So we've got this. So this number here is so small you can forget about it. 1 minus a very small number is just 1. So this becomes 10 times 1 over 1 minus 1/2, which is 20. So this series here, if you add them up, you get 10 plus 5 is 15, 17.5, 18 3/4, and so on. In the end, that number is going to be equal to 20. This is a demonstration of the sum of an infinite series, which is a 1 minus r to the n over 1 minus r. That's what that's the formula we had for Sn. But if we take an infinite number of terms in the sequence, then r to the power n is going to be 0, with one condition, which I'll come back to in a minute. So we can now say this equals a over 1 minus r. Now that only works if mod r is less than 1. What does that mean? That means that r is between 1 and minus 1. Why is that? Because if r is between 1 and minus 1, r to the power n is going to be approach 0. If r was 2, then 2 to the power n would be a very large number. 2 to the power 100 is a massively large number. It's 1.3 times 10 to the power 30. But if the r number, the common ratio, which in this case is 1/2, if that's between 1 and minus 1, when we raise it to a very large power, then we get the fact that r to the power n is 0, which is what we had here. So what about this geometric sequence here, or this geometric series here? The series is when you add the numbers together. What is the sum to an infinite number of terms? Well, the first term is 30. The common ratio is 27 over 30, which is 0.9. You can check that by doing 243 over 10 divided by 27, and you'll still get 0.9. Or 2187 over 100 divided by 243 over 10, you get 0.9. So the sum to an infinite number of terms is a over 1 minus r. So that's 30 over 0.1, which is 300. So that's pretty quick, pretty amazing. I've added up all these terms, and I've added up an infinite number of them in the space of about 300 milliseconds to get the answer 300. So the formula s, let's get this right, s to infinity is a over 1 minus r, as long as the actual value of r is less than 1, is a very powerful formula.